Now that you're masters of drawing Lewis structures, it's time to start looking at these molecules in 3 dimensions. Lewis structures are great. They show how the valence electrons are shared so that all atoms get an octet, at least the atoms that want an octet. But Lewis structures do not represent the true 3-dimensional shape of these molecules, which molecules are 3-dimensional, so that matter is 3-dimensional. To figure out 3-dimensional shapes of molecules, we use something called the Vesper theory. Now this sounds very impressive. It's called the valence shell electron pair repulsion theory. Go home and tell your parents that you had a big day. You learned the valence shell electron pair repulsion theory. It really makes sense though. When we're looking at Lewis structures and these 3-dimensional shapes of molecules, we are concerned with electron pairs in the outermost valence shell. We've never drawn electron dots in the inner orbitals or the inner energy levels. All of those orbitals are full, they're stable, they're not involved in bonding. It's the outermost valence electrons that are involved in bonding and give us these 3-dimensional Vesper shapes. So here's what we do. We draw the Lewis structure. We look for electron pairs in the outermost valence shell. When we find those electron pairs, since they're all negatively charged, they repel. And they'll orient themselves as far apart as possible. And that's what gives us the bond angles. Hence, the valence shell electron pair repulsion theory. Electron pairs in the outermost valence shell repel. They'll orient themselves as far apart as possible and give us 3-dimensional shapes of the molecule. When we do these 3-dimensional models, we usually start with a Lewis structure. So for example, this beryllium molecule, this would be an easy Lewis structure. Beryllium only has 2 valence electrons. 1, 2. And we usually said put them on opposite ends of the beryllium to show that electrons are negative and like charges repel. Well, then I'd add the 2 fluorine with his 7 valence electrons, kind of lining up the singles. Connect the dots. And here's the other fluorine. 1, 2, 3, 4, 5, 6, 7. Link them up. There we go. Now a couple things. Number 1, the fluorines do have an octet. They have 6 non-bonding electrons and 2 electrons that are bonded. The center beryllium does not have an octet, and that's okay. Early on we mentioned that there are some atoms that are stable with less than an octet. They're called deficient octets. Beryllium is a good example. We don't have any more electrons to give the beryllium, so he's going to have to deal with 4. And in the end, it's okay. The beryllium is stable with just his 2 valence electrons bonded. So you don't have to overthink them. You link on the 2 fluorines, it's a done deal. That's all the electrons we have. Beryllium is a deficient octet. Now to get the 3-dimensional Vesper shape, we're really concerned with electron pairs on the central atom. And we're going to put them into one of 2 groups. These electron pairs on the central atom could be bonding electrons. So I'm going to put these as bonding electron pairs. They could be bonding electron pairs, which then kind of gives us a measure of how many atoms are bonded to the central atom. Or they could be lone pairs of electrons around the central atom. We're concerned with the central atom. Lone pairs are non-bonding electrons. And again, concerned with the central atom. What kind of electrons are on the central atom? Are they bonding electrons or are they non-bonding electrons? So I look at my beryllium. and I have two groups of bonding electrons. Those two groups of bonding electrons are all negatively charged. They'll repel and orient themselves as far apart as possible. Here's kind of a good ball and stick model. This angle is 180 degrees. The two fluorines will go as far apart as possible. 180 degrees, we call the shape linear. Well, duh, it looks like the atoms are all in a line. Whoever came up with that name was brilliant. Yeah, it's linear. Another good example, carbon dioxide. Carbon has 4 valence electrons. 4. We hook on the oxygen. We try to line up the singles. Oxygen has 2 singles and 2 pairs. Connect the dots, connect the dots. And then I kind of do the same thing with the other oxygen. We'll line up the singles, give them as pairs for a total of 6 valence electrons. Connect the dots. 2 double bonds. And again, we mentioned earlier that there's not a whole lot I can do to try to trick you on a test or quiz. You know, if I gave you silicon dioxide, it looks exactly the same. Or I could give you carbon disulfide. It looks exactly the same. If the elements are coming from the same group on the periodic table, they have the same number of valence electrons, they form the same kinds of bonds. Now, if you get really good at drawing these Lewis structures, or maybe you've said, I've drawn carbon dioxide 1,000,000 times, you might know that it's double bonds. You can just give me 2 dashes. As long as you put the electron pairs on oxygen, and I don't care where they go. Top, bottom, sides, I don't care. We just have to prove that oxygens have an octet. So both of those are totally acceptable. I'll understand that whenever you show me a dash, it means 2 electrons shared. 2 dashes, then, would be 4 electrons shared, a double bond. So in either of these pictures, we've got our central carbon. There are 2 electron regions around that carbon. Now they happen to be double bonds, which means there's 4 electrons, which is kind of irrelevant. They're electron regions. And electrons are all negative. Whether you have 2 electrons or 4 electrons, they're all negative. They'll repel. They'll orient themselves as far apart as possible. This molecule is linear. The shape, this Vesper shape, is not affected by a double bond versus a single bond or even a triple bond. We're just looking for electron groups. Whether it's 2 electrons, 4 electrons, 6 electrons, that doesn't matter. Carbon dioxide is linear. Another good example might be HCN. HCN. The carbon in the center has 4 valence electrons. Hydrogen has 1. We can single bond the hydrogen. Nitrogen has 5 valence electrons. I'm going to put the 3 singles toward the center and then the pair on the outside because I want the single electrons to match up. That's where we share electrons. So here's my hydrogen cyanide, HCN. A single bond and a triple bond. However, it's still linear. Here's an electron group. Here's an electron group. Now one group has 2 electrons, the other group has 6, which again is irrelevant. It's 2 groups of negative electrons. They're both bonding groups of electrons. They'll repel, go as far apart as possible. This molecule is linear. So again, it doesn't matter that one is single and one is triple. They're still counted as electron regions. They're all negative. They all repel. Cute. Now, I guess one more thing that we should mention, too. Sometimes you'll get these real simple molecules like hydrogen, diatomic hydrogen. Well, technically, there is no central atom. But how else are you going to connect 2 hydrogen but in a line? So it may not follow this chart where it's asking about how many atoms are bonded to the central atom, but it's linear. Same thing if I did like a hydrogen and a fluorine or something like that. Hydrogen, fluorine. It doesn't matter if the atoms are different. It's two atoms. You connect them with a line. You have no other option but to make this linear. So linear molecules are very simple. There will be two other atoms bonded to the central atom, or there will be two regions of electrons around the central atom, and no extra lone pairs on the central atom. All electrons in the central atom are bonded. And then we've got these little simple molecules that only have two atoms, and they have no other choice but to also be linear.